Okay, so what we're dealing with right now is we're working on solving non-homogeneous differential equations. Non-homogeneous second order linear differential equations. Or in other words, y double prime plus p of t y prime plus q of t y is equal to g of t. And mostly we're dealing with the case where the coefficients p and q are constant functions, namely numbers. So can someone kind of summarize what we discussed yesterday for how our approach is for solving non-homogeneous differential equations?
So we just find like the homogeneous fundamental set and a particular general solution.
Exactly. Yeah, thank you. So the idea is the general solution to L of y is equal to g of t, where here L is once again second order homogeneous differential operator, looks like C1y1 plus C2y2 plus capital Y, where y1 and y2 are a fundamental system for L of y is equal to 0, and all we require is L of capital Y is equal to G of t. Right? All we need to get the general solution to the non-homogeneous differential equation is to write the general solution for the homogeneous plus a particular solution. So we already pretty much know we have all the low-hanging fruit in terms of the general solutions to homogeneous differential equations that we can find. So the real question now is how to find y. And the method that we discussed yesterday was the method of undetermined coefficients, is what it's called. And that's a fancy name for just guess. So method 1, undetermined coefficients. In parentheses, educated guess. And the basic idea is that if g of t is a polynomial, what should you guess?
A polynomial of the same degree of g of t?
Exactly. Try a polynomial of same degree. And in particular, when I say try a polynomial of the same degree, what I mean is take a polynomial, but leave the coefficients as variables, right? So in particular, if g of t is like 3t plus 4t squared, I suggest your guess looks like a plus bt plus ct squared, and you plug that in and solve for a, b, and c. We did this yesterday, so I'm not saying anything new. If g of t is an exponential function, what is our guess?
An exponential function.
Yeah, try an exponential function. And what if g of t is either sine or cosine, or something related to sines or cosines? Say beta sine of alpha t.
You want to try a constant times sine plus a constant times cosine?
Yes, exactly. And we want to make sure that we have whatever constant is in the argument, we want to preserve that. So try, what will I do? I'll call it P1 times sine of alpha t plus P2 times cosine of alpha t, where p1 and p2 are variables that I have to solve for. Okay? Any questions on this material that we went over yesterday? Okay, great. So what we're going to do today is move on to the next method, which we won't spend too much time on. So method number 2 goes as follows, and it's called the method of variation of parameters. Here's what I want to say about the variation of parameters. For the undetermined coefficients, basically what you're depending on, or what you're using on, is that derivatives of these functions look like the same function. Namely, derivatives of polynomials are always polynomials, derivatives of exponential functions are always exponential functions, and derivatives of sine and cosine will always be combinations of sine and cosine. But we can only expect this kind of naive method to work when we have that property. And most of the functions that we deal with don't look like their derivatives, right? Like natural log of cosine of t, that's something that could appear as g of t. What are you supposed to guess for g of t if g of t is a natural log of cosine? Because you shouldn't guess something in terms of natural log of cosine, because the derivatives of natural log of cosine will be all sorts of weird things, you know, like 1 over cosine and stuff like that. 1 over cosine times the derivative of sine. So you're going to get, in general, complicated stuff. So the method of undetermined coefficients is useful in these very narrow cases when g of t is like this. Variation of parameters can be tried much more generally. That is, if you've got some g of t that's not one of these, you could try variation of parameters. Okay, here's the idea. What we want to see is, like, say y1 and y2 are a fundamental system for L of y is equal to 0. Namely, this is a fundamental system for the homogeneous piece of the differential equation. What variation of parameters tells us to do is, let's try to find a solution to L of y is equal to g of t by replacing the constants in front of y1 and y2 in the general solution with functions by or of the form u1 of t y1 plus u2 of t y2. So whenever u1 and u2 are constants, you know that this will be a solution to the homogeneous part of the differential equation. And the guess is that maybe there's some function that we can put here such that this differential equation, or such that this solution will solve the non-homogeneous differential equation. In other words, maybe we can find some functions u1 and u2 that differ just enough such that when I take the derivative here, I get back the non-homogeneous piece g of t. Does everyone understand kind of what this guess is about? Does anyone have any questions right now?
Looks good for me.
Looks good? Okay, great. Okay, so let's examine some of the ramifications here. Well, first, before I flip the page, I'm trying to solve one differential equation. I've got one equation, namely L of y is equal to g of t, and two functions, namely u1 and u2. Right? A priori, I'm trying to solve for the functions u1 and u2, but I've only got one equation. What do we generally know about trying to solve for two terms only given one equation?
It well usually doesn't work out. You might get like a function.
Right, exactly. Probably all that will happen is I'll be able to write u1 as a function of u2, but I won't be able to determine either of them uniquely, right? Or another way to look at this is if I were somehow able to introduce a second equation in terms of u1 and u2, then maybe I could solve for u1 and u2 more or less uniquely, because if I've got two equations and two unknowns, then I have a chance of solving them. So our idea should be, I've got one equation on u1 and u2 determined by, it needs to be a solution to the non-homogeneous differential equation. And what we should kind of be thinking about is maybe there's a nice second equation involving these two that we can enforce to make things calculable. Is that kind of clear what I'm saying?
Yeah.
Great. So now comes a kind of a tedious calculation. So explicitly, we are trying to solve y double prime plus p of t y prime plus q of t y is equal to g of t. And now I have the kind of hypothesis, like I want to try out the function y is equal to u1 y1 plus u2 y2, where once again, everything's a function of t, but that gets so annoying to write all the time, so I'm just going to write it this way. Well, what I need to do is I need to plug in this function into this differential equation and see what I get. So what I'm going to do first is I'm just going to calculate the derivatives of y. In particular, the first derivative of y is going to be equal to u1 prime y1 plus u1 y1 prime plus u2 prime y2 plus u2 y2 prime. Okay. If I start here and then take a second derivative, because I need a second derivative, then I'm going to have 8 terms and I'm going to have a total mess, right?
Yeah.
So here is where there's a very nice insight, which is due to Laplace. Remember that we are also kind of hunting around for a second equation involving either u1 and u2 or their derivatives, because we've got two unknowns, namely u1 and u2, but we only have one equation relating them so far. So the idea of Laplace was, I can kill two birds with one stone. I'm going to introduce a new equation relating my variables u1 and u2 or their derivatives, and I'm also going to make my life simpler. In particular, I want my expression for y prime to be nicer. So here we introduce a new relation or a new equation, and we demand that u1 prime y1 plus u2 prime y2 is equal to 0. So here is some thoughtful math that's happening. In general, if you only have one equation and two variables that you're trying to solve for, you could get a huge family, and you won't be able to determine one in terms of the other. So we kind of have some freedom in terms of what equations we want to impose, such that we can hopefully get an actual solution. So the cleverness here is imposing a second equation, here involving the derivatives, such that our calculations become much nicer. So it's killing two birds with one stone. So with that in mind, now, after this equation, which I'll call star, then y prime actually becomes u1 y1 prime plus u2 y2 prime. So this is an important thing that you should remember when you're thinking about this technique of variation of parameters, first you should start with a function like this, where y1 and y2 are a fundamental system for the homogeneous piece. Multiply them by some random functions that are undetermined, but then make the condition that when you take the derivative of y, the terms involving u1 prime and u2 prime must cancel each other out. Then y prime is equal to this, and this means that y double prime is therefore going to be equal to u1 prime y1 prime plus u1 y1 double prime plus u2 prime y2 prime plus u2 y2 double prime. And I'll call this equation star star.
Is it possible that making that demand that like those two terms cancel, that it like restricts us from finding a solution sometimes?
My impression is that if all of the functions that you're dealing with are differentiable, the answer should be no. So I think that the answer is that you shouldn't be cutting down too much in the space of solutions by imposing this restriction.
Okay, thank you.
I mean, yeah, I believe that should hold. Okay. So now these are the two equations that we want to solve for, and let's now plug in. So what we have is we have this big thing for y double prime. So u1 prime y1 prime plus u1 y1 double prime plus u2 prime y2 prime plus u2 y2 double prime. Now I need to start adding back plus p of t times y prime. Y prime is now just u1 y1 prime plus u2 y2 prime plus q of t times y, which is u1 y1 plus u2 y2. And we want to set this whole expression, all three lines, equal to g of t. Do we agree that this is just what we get when we plug in this new kind of potential solution into this differential equation?
Yeah.
Okay. Now, what I want you to examine is the following. Let me kind of try to trace out what I've got here. I've got a term here that looks like u1 y1 double prime plus u1 p of t y1 prime plus q of t u1 y1. What is this?
You just separated the y1s from the equation above?
Yes, but remember, what was my assumption about y1?
y1 was the solution to the homogeneous equation?
y1 is a solution to the homogeneous equation, which means that this line is equal to u1 times L of y1, right? y1 double prime plus p y1 prime plus q y1. What is this thing?
0.
This is 0, exactly. And I can also do that over here. Here I've got the same sort of thing happening with the u2 times y double prime. I've also got plus u2 times y2 double prime plus p y2 prime plus y2 q of t y2. And this is also equal to 0. So all that I'm actually left with is u1 prime y1 prime plus u2 prime y2 prime being equal to g of t. In other words, my big bad differential equation, when I plugged in y and I got this massive thing, actually most of it simplifies. I'll call this, I don't know, triple star. So now let me put my original expression star and triple star side by side. u1 prime y1 plus u2 prime y2 equals 0.
Could you move the paper up?
Oh, yep, sorry about that. Thank you. So the point is that when I started off by saying, let's find out when is this a solution. I made the assumption star, which cut down on the number of possible solutions, y1 in terms of y2. The only chance that we have of actually finding solutions y1 and y2 are if we make some equation relating them. And now what we've gotten, we've boiled it down to two equations where essentially we're trying to solve for u1 prime and u2 prime, right? Here, it seems plausible that using these algebraic equations where we write u1 prime y1 prime plus u2 prime y2 prime is equal to g of t, and u1 prime y1 plus u2 prime y2 is equal to 0, it seems plausible that we could actually write out or solve for u1 prime and u2 prime. Is this reasonable? Is this believable, what we've done so far?
Yeah.
Okay. And notice, this was an assumption that we made. And this assumption we made so that our calculation became easier. And after we made this assumption, this is what the whole differential equation boiled down to. So these equations are not, given to us. They're not forced on us. These equations result because we made the choice of this equation to simplify our calculations. Okay, I've run out of paper on this notepad, so it's time for a new one.
I had a question.
Oh,
So
yeah,
for
sure.
our star assumption, can we not
Yes.
say that because the y1 and y2 are solutions that they should be 0?
So y1 and y2 are solutions to the homogeneous differential equation, but that almost guarantees that they're not solutions to the non-homogeneous differential equation.
Okay.
Does that help?
Yeah, thank you.
Right. When I plug y1 and y2 in over on this side, I'll get 0, and that's probably not equal to g of t unless g of t is 0. Yeah. Okay, let's solve a little further with this kind of abstract notation. So let me rewrite the two equations here. We've got equation u1 prime y1 plus u2 prime y2 is equal to 0. This is equation star. And then I've got equation u1 prime y1 prime plus u2 prime y2 prime is equal to g of t. This is equation star, star, star. And what I can actually do is I can genuinely try to use like substitution to solve this system of equations. So let me do that. Let me write the following. Let me start with the top equation, and I'll write then that u1 is going to be equal to, let's see what we get here, u1 prime is going to be equal to, I subtract this over, u2 prime y2 all divided by y1. This is what I get by solving for u1 prime inside equation star. Do we agree?
Yeah.
Okay. Now what I'm going to do is I'm just going to do the normal substitution method. Once you use one equation to solve for one of your variables, you plug it into the other equation. So plug in to star, star, star. And what I get is negative u2 prime y2 over y1 times y1 prime. I know it's getting kind of messy and confusing, but it'll simplify in a moment. Plus u2 prime y2 is equal to g of t. Remember, oh, yes?
Y2 prime?
Here it is indeed y2 prime, thank you. And remember, we're trying to solve for u of 2 prime. And so what we should do is we should get a common denominator. We should divide by y1, and we should factor out a u2 prime. So factor out u2 prime and common denominator. And what I get is u2 prime times, what I'm going to get here is y2, y1 prime. Oh, sorry, this should be a negative. Oh no, oh no, oh no. What I should get is u2 prime times, here I have a y1, y2 prime, minus, now I have this side, y2, y1 prime, all over y1 is equal to g of t. Or, in other words, if I want to just solve for u2 prime, I get u2 prime is equal to g of t times y1 of t divided by, what is this thing? y1, y2 prime minus y2, y1 prime.
It's a product rule.
I don't disagree,
Almost.
but
It's the opposite of a product rule.
it is a determinant. It is a Wronskian. y1, y2 prime minus y2, y1 prime, remember? y1, y1 prime, y2, y2 prime. Determinant of this, y1, y2 prime minus y2, y1 prime. Oh, look at that. Math is beautiful. Okay. So I am aware that I have done a lot of algebraic manipulations with a whole mess of symbols, and it has seemed very abstract and probably uncomputable. But what we have arrived at is me saying, if we make the assumptions that we made, that is, we assume star, and then we produce star, star, star from plugging into the differential equation, we can literally solve for u2 prime. And it's literally going to be equal to the non-homogeneous piece times one of your first fundamental solution over the Wronskian. And all of these things are either given to you, g of t is given to you, y1 you can obtain because we're assuming you can solve the homogeneous second order linear, and the Wronskian you can compute. Similarly, you do this whole calculation, but instead of solving for u2, you solve for u1 prime. We also get u1 prime is equal to negative y2 g divided by the Wronskian of y1 and y2. In other words, I have found differential equations only in terms of t. So these are as I say often, these are Calc 1 problems, not differential equations problems. I've literally found expressions in terms of t for the derivative of u1 and the derivative of u2, such that if I take antiderivatives here and antiderivatives here, I will get functions u1 and u2, such that that will give the general solution to the differential equation. Any question here?
I'm confused. I think I missed how you got the u prime of 1 equation.
I did not show you that because it's essentially the steps. So here's what happens. I only really showed you how to get the u2 prime. You get the u2 prime by starting with this equation and getting u1 prime all by itself, and then substituting in for star, star, star. Substituting in u1 prime for star, star, star. And then you get an equation for u2 prime. If you do the other way, and you start by isolating u2 prime in equation star, then you plug that into this equation, then you get an equation only in terms of u1 prime, and that'll give you this. So I didn't show you how this one goes, but it's the same steps that I did for this one, just changing which variable you're solving for.
Okay, got it. Thank you.
Yeah. Okay. So then if you actually want to literally solve the differential equation in terms of elementary functions, the question becomes, is this function expressible in terms of elementary antiderivatives? But like, remember that for the purpose of this class, it's fine if you can't find an antiderivative in terms of elementary functions. You can always just use the first fundamental theorem of calculus and say, I can take antiderivatives of this function. So let's do an example. Let's solve y double prime plus y is equal to tangent of t. Notice already that I am in no mood whatsoever to try the undetermined coefficients method with this non-homogeneous differential equation, because the derivative of tangent is secant squared, and the second derivative of tangent is going to be whatever happens when you apply the product rule to secant squared. It's going to be something terrible. And I also don't have a good way of thinking about antiderivatives of tangent. I don't know a function which is the second antiderivative of tangent. So already the method of undetermined coefficients, or the methods of an educated guess, are right out for me here. I'm in no mood to try to guess what a solution could look like. However, all this work that I did beforehand tells me that there are functions u1 prime and u2 prime that I can actually calculate such that I can get a general solution. So here, if we're doing variation of parameters, the first thing that I need to do is I need to find a fundamental system of solutions for the homogeneous piece. What's the characteristic equation of this homogeneous piece?
R squared plus 1.
Yeah, this is going to be x squared plus 1. So the roots are going to be
I.
and negative I. Remember that when I've got complex conjugate roots, I only need to take one. So a solution is e to the it. And what does that give me in terms of my two real solutions?
Cosine of t and sine of t.
Yeah, cosine of t and sine of t are a fundamental system. So I'll call this y1 and I'll call this y2. Now I should compute the Wronskian of these two. What's the Wronskian of these two functions? Well, it's the determinant of cosine of t, negative sine of t, and sine of t, cosine of t. I'm sorry, I will move it up. There you go. What's this determinant?
1.
Yeah, is equal to cosine squared plus or minus minus sine squared, which is equal to 1. Well, that's very pleasant. It's almost like I probably chose this problem specifically because it was nice. Okay, what does variation of parameters now tell us about u2 prime and u1 prime? So now let me say it as follows. Variation of parameters says u1 times cosine of t plus u2 sine of t is equal to g of t if, and it's not an if and only if, it's just an if. There are many other options. This option is the option that I get because of the assumption star. So what I need to require is that u1 prime is equal to this thing and u2 prime is equal to this thing. In particular, u1 prime should be equal to negative sine of t times tangent of t. And u2 prime should be equal to cosine of t times tangent of t. Well, u2 prime is easy to solve for, right? u2 prime, cosine of t times tangent of t is just sine of t, right? Tangent is sine over cosine. So really I can write this as u2 prime is supposed to be sine of t. Does anyone know the... Oh,
That.
Sorry?
How did you get there? How did you get u1 prime and u2 prime?
I got u1 prime and u2 prime because variation of parameters tells me that if I want, well, let me go, well, I shouldn't go all the way back, but I'm getting it from these two equations. What I did in this whole abstract thing is I said, when is u1 y1 plus u2 y2 a solution to the non-homogeneous? Namely, if you take all the derivatives, you get g of t. I made assumption star. I produced from that a second equation, star, star, star. I use these together to solve for the conditions. So if the derivative of u2 is this function, and the derivative of u1 is this function, then u1 y1 plus u2 y2 is a solution to the non-homogeneous differential.
Okay, so you like did all the calculations for that.
Yeah, right. So I did all the heavy lifting to find formulas for the derivatives. And then here, what we did was we found all the pieces. First, we found a y1 and y2, namely solutions to the homogeneous piece. Then we calculated their Wronskian. Turns out the Wronskian is super nice. And I just plugged all of that into these expressions. So tangent of t is g of t. Negative sine of t, or sorry, these match up. The Wronskian is 1, g is tangent, negative y2 is negative sine. And then these two match up. The Wronskian is 1, g of t is tangent, y1 is cosine.
Okay, thank you.
It's a little complicated, I agree. But in any case, I then produce these two functions as derivatives. So u2 prime is equal to sine of t. So what should u2 be?
Negative cosine.
Negative cosine plus a constant. Yes. Does anyone know what the antiderivative of negative, well, really the antiderivative of sine times tangent? This is almost certainly one that you can compute either using u substitution. Right? This should be a u substitution. This is sine squared over cosine. So you make a u substitution of u is equal to sine, and its derivative will be cosine. Things will cancel. You'll get something nice here. What I'm saying is in this case, it's computable what u1 and u2 are. In general, who knows? In general, maybe I just have to write antiderivative from t0 up to t of negative sine of x tangent of x dx, and antiderivative from t0 up to t of cosine of x tangent of x dx. But the point is, I have been able to write the derivative of u1 as a function of t and the derivative of u2 as a function of t. This is like the maximum amount of control that you could possibly ask for. We have determined options for u1 and u2. Any questions on this?
All good.
Great. So since examples are always good, I'll let you compute an example briefly, and then we are going to move on. I'm not going to spend too much time on the variation of parameters.
Wait, I'm sorry, I actually do have a question.
Yeah, great.
So when you finally get your u1 and u2, what's the final form that we're supposed to be writing the solution in again?
Yeah, that'd be a great thing for me to write. Let me do an example here. So actually, if somebody could actually look up the concrete antiderivative of sine tangent, that'd be lovely. I don't want to compute it right now. No, it's not hard. But what we found is u2 prime is equal to, what was it, cosine of t? u2 prime, no, sine of t. So we conclude that u2 is equal to negative cosine of t plus c1. And then u1 prime is equal to negative sine of t tangent of t. Anyone have the antiderivative for me?
I think it's negative 1/3 times sine cubed t.
Negative 1/3 times sine cubed t plus c2. Very good. Yeah, that's exactly what you get if you do the u substitution, because then you're going to have a sine squared over the derivative of sine. So what this tells me is that the general solution to L of y is equal to, or let me write it out explicitly, y double prime plus y is equal to tangent of t is equal to 1/3 sine cubed of t plus c2 times cosine of t. This is the y1 and this is u1, plus over here negative cosine of t plus c1 times sine of t. Here is y2, u2. General solution looks like this. And if you want to
just to say,
have I done something wrong?
It's just a negative in the first term in case somebody looks back at it.
Oh yeah, good point. This should be a negative 1/3. Is that what you're saying?
Yeah, that's right.
Okay, thank you. And if you want to, you can simplify this all the way back to what we know the solution has to look like. In particular, this can be rewritten as c2 cosine of t plus c1 sine of t plus, and now here's the specific solution, negative 1/3 sine cubed of t cosine of t plus negative cosine of t sine of t. The point is, this is our specific solution. Here's our general solution for the homogeneous piece. I would not have been able to guess this solution as a specific solution to the non-homogeneous differential equation using the what's it called? The undetermined coefficients method. But I still was able to use this variation of parameters method to find a specific solution. It's just the way that we went about it was via a different process. Does this answer your question?
Yes, thank you.
Yeah, sure. Okay, is there an exercise that I can give you? Yeah, why don't you try this one? And despite the fact that I did do some I did do some interesting math to derive these two equations. But now that I've derived these two equations, you can just use this to immediately know what u1 prime and u2 prime ought to be. So in this case, I would say don't find the general solution, but find u1 prime and u2 prime such that u1 y1 plus u2 y2 is a general solution, or is a solution to y double prime plus 4y prime plus 4y is equal to t to the negative 2 e to the negative 2t. So why don't you give this one a shot for some practice?
Wait, does that say 4y prime plus 4y?
That's correct.
Okay.
In particular, I did give you a repeated root homogeneous piece. So can someone tell me the or a set of fundamental solutions to the homogeneous piece?
I got C1 e to the negative 2t plus C2 t e to the negative 2t.
T e to the negative 2t. Yeah, exactly. This should be a fundamental system of solutions. Did you all get that?
Yeah. Yes.
Okay. So then the next step, if we want to compute these terms, is what?
Compute the Wronskian.
Yeah, we need the Wronskian. So the Wronskian is going to be det of e to the negative 2t. And down here I'm going to have negative 2 e to the negative 2t. And here I'm going to have t e to the negative 2t. And here I'm going to have e to the negative 2t plus negative 2t e to the negative 2t. And did anyone compute this determinant? My impression is that it should be e to the negative 4t.
Yeah.
Right? The e to the negative 2t times e to the negative 2t will survive. The e to the negative 2t times this term will cancel when I subtract off what I get from the anti-diagonal. So I'll be left with e to the negative 4t. So what we immediately know is that u1 prime is going to be equal to what? Negative y2. So negative y2 is negative t e to the negative 2t times g. What is g in this setting?
T to the negative 2 times e to the negative 2t.
All over the Wronskian, which is e to the negative 4t. And what we produce here, by some miracle, is negative 1 over t. The e to the negative 2t and the e to the negative 2t on top will cancel with the e to the negative 4t on the bottom. I'll be left with negative t times t to the negative 2. So u1 prime is going to be natural log of t. Wait a second. Natural log of absolute value of t.
That's just u1, right?
Yeah, u1.
Okay.
I need to take a negative here. We can make assumptions about whether t is positive or negative, but the idea is u1 should be negative. Actually, probably we can just do negative natural log of t and assume that t is positive. So we found u1. Let's consider u2 prime. It's going to be the same procedure. From our formula via variation of parameters, what should u2 be?
Do you want u2 prime or u2?
First, let's do u2 prime.
Okay. It will work out to 1 over t squared.
E to the negative 2t, I trust you, but I just haven't done this. So times g of t, which is t to the negative 2, e to the negative 2t, all over e to the negative 4t. And this will work out to be 1 over t squared, right?
Mm-hmm.
And then this implies that u2 is going to be negative 1 over t. Did I do that right? Well, plus c here and plus c2 here. Did everyone get this?
Yeah.
Yep.
So in this fashion, we find the general solution. General solution will be negative natural log of t times whatever my first solution was, e to the negative 2t, minus 1 over t times t e to the negative 2t, plus, and now I do the general solution for the homogeneous piece, c1 e to the negative 2t plus c2 t e to the negative 2t. And this is my general form, or my general solution, for this non-homogeneous differential equation. And this is just u1 y1 plus u2 y2. I just expanded out.
Did you forget constants in the first two terms, or do you like carry them over to the last two?
I separated them out to here. Yeah, if you looked at this, if you had negative natural log of t plus c1, and you multiply that by y1, I don't think I made mistakes here. So should I do this more carefully?
No, that's all good.
Okay. So the main idea is that we have two methods to solve non-homogeneous differential equations. One works quite easily when the function g of t is one of these kind of special functions whose derivatives all look alike, namely polynomials, sine or cosine, or exponential functions, or combinations thereof, sums, combinations thereof, right? And if g of t is more complicated, then you might need to use variation of parameters. And one thing that I want to point out too, for instance, and I just want to move on after I point this out, but going back to the, if you have L of y is equal to g1 of t plus g2 of t, so I'm saying g can be broken up as a sum of functions. Do you remember how you approach this one?
You just say L of y equals g of 1, or L of
Yeah.
y1.
Find a y1 such that L of y1 is equal to g1, and a y2 such that L of y2 is equal to g2. Then y1 plus y2 will be a particular solution to apply the differential equation and get g1, g2. And L of y1 plus y2 is equal to g1 plus g2. So if you get some complicated function of g, some complicated function g on the right-hand side where it's a sum of several functions, break up that sum, find particular solutions for each non-homogeneous piece, and then add them all together, and you'll get a particular solution to the whole thing. And then you just add that on to the general solution for the homogeneous piece, and you're done.
Okay, I'm sorry, I just want to make sure I'm clear. So the general solution is literally just u1, y1 plus u2, y2, right?
Here, when I'm doing variation of parameters, I have two options. Either I can take antiderivatives of u1 and remember that I could add a constant, and then take an antiderivative of u2 and add a constant. And when I have u1 being this family of functions and u2 being this family of functions, then I get the whole general family. Or I could set c1 equal to 0 and set c2 equal to 0. In this case, that would kill this part. And now this, what's left over, is a particular solution to L of y is equal to g of t.
So, okay, why is that different from what we did in the previous example? Or is it?
I am not sure I exactly understand your question.
I think I might be wrong, but I think the question is, you know how before we had the homogeneous solution and then we like tacked on that extra term? We don't do
Yes.
that here, right?
What I'm saying is, if you, so here's what I could say. In the homogeneous, in the undetermined characteristic or undetermined coefficients, the steps were 1, find c1 y1 plus c2 y2 a solution to the homogeneous. Step 2, find particular solution big Y. So then 3, c1 y1 plus c2 y2 plus big Y is our general family. Okay, what variation of parameters does is it gives us u1 prime and u2 prime such that u1 y1 plus u2 y2 is a solution for any antiderivative of u1 prime and u2 prime. So for instance, if let's say u1 prime was equal to, I don't know, like t, and u2 prime was equal to t squared. Then a particular solution is t squared over 2 times y1 plus t cubed over 3 y2, right? I took one of the many antiderivatives of these two functions, and then I know that this is a particular solution. Do you agree with what I've said thus far?
Yeah.
I forget who asked this question beforehand, but
It was me. I'm sorry. Can you not hear me?
Alapika, I can hear you. Yeah, I didn't hear you if you responded, but is this okay?
Yes.
Okay. Now, a general solution, or the general solution, can also be found by taking the most general antiderivative of t, which is t squared over 2 plus c1 times y1, and the most general antiderivative of t cubed over 3, which is t cubed over 3 plus c2 y2. Now, this will also be a solution for any choices of c1 and c2 by the exact same rule. Anytime that the derivatives are t and t squared, I know that this will be a solution. That's what I did all that work in variation of parameters for. So you agree that this looks like a general family?
Yes.
Now the point is, if I distribute, then I get t squared over 2 y1 plus t cubed over 3 y2, which is the particular solution I found up here by letting c1 and c2 be 0, plus c1 y1 plus c2 y2, which is the general solution that we expect to the homogeneous piece. So the point is, you get the same thing either way, but if you do the variation of parameters, you can kind of find the general solution all at once instead of first finding a particular solution and then tacking it on.
Okay, I think I understand now.
Right? Like this is the expected answer, and this was the answer we got. And what I'm trying to say is they're equal, they're equivalent for all intents and purposes.
Okay, that makes sense. Thank you.
Yeah, sure. They're good questions. Okay, any other question on this material, on this non-homogeneous differential equations? Okay, what I'm going to do next is we're going to get started into the next section, which at this point, I forget what number this is going to be. Is this 3.6 or 3.7? The one with the harmonic oscillators. I can look it up in just a second.
It's 3.7.
3.7, okay. Next, 3.7. So we've spent a whole bunch of time just doing pure differential equations. But now that we can essentially solve second order linear homogeneous differential equations, it turns out that second order homogeneous linear differential equations pop up all the time in physics. So the point is, second order homogeneous, sorry, I don't want to require it to be homogeneous. Second order linear differential equations appear all over physics. Essentially, second order linear I'm like broken. Second order linear differential equations model oscillations. So the idea is these should model oscillations. And the kind of oscillations that you find are mass systems on springs, mass on spring, a position or like a equation of motion of a particle on a vibrating string, or electrical current in a circuit. So if you've taken some physics, it is assured that you have kind of at least been shown a second order differential equation and then told what the solutions are and then examine those solutions carefully. So we're going to do a little bit of that. So we're going to have kind of an applied section. And all of these are governed by a differential equation that more or less looks like a y double prime plus, well, let me write p of t y prime plus q of t y is equal to g of t, which at this point we are extremely familiar and probably sick of this differential equation. Okay, so let's first kind of go over some of the physics. So we're going to examine the physics of a mass spring system. Okay, so the idea here is we have some spring which isn't coiled up perfectly tightly. So what this means is that if you take the bottom of the string and you compress this string, if you compress this spring, it'll push back on you. And if you pull on this spring, it will pull. So we want something that if you compress it, it'll push back, and if you pull it, it'll pull. And let's say that just on its own, this spring has a length L. Okay. Then let's say that we attach a weight to this spring. There's going to be some equilibrium position where this system is not in motion, where it's just still. So if you do the free body diagram for this, you're going to try to add up all the forces. And since the motion is zero, the acceleration is zero. So what that's going to tell us is that, well, what is the force downwards? Or for us, if down is the positive direction, what is the force that is in this direction?
G.
Yeah, gravity is going to be pulling on the mass. So down here, I'll have the force downwards being mass times gravity. The force upwards is essentially provided by the spring. So here is an experimental observation called Hooke's law. When a spring is compressed or extended by a small distance, then the force is proportional to the distance. In other words, the resting, or kind of if there's no mass on the spring, its kind of resting neutral state is to be at length L. But here, its resting, the equilibrium state is going to be when the spring is at length capital L. And Hooke's law tells us that the force in this direction should be proportional to L, or that I should write here negative KL. We okay so far with this physics magic that I'm talking about?
Wait, L is the length, like capital L is the length when it's like moving and not at rest, and cursive L is like when it's at rest?
Not quite. Capital L is when it's at rest, but with a mass. So you can imagine attaching a mass, it'll probably wobble and oscillate back and forth, and then if you leave it for 10 years and come back, it'll be totally still. And the capital L is the kind of new length of the spring in an equilibrium when it's not moving, but it is stretched down by the mass. Right, so this free body diagram assumes that nothing is moving here. Is that okay?
Yeah, thank you.
Okay, so by Newton, this system is not moving. So what I get is that mg minus KL is equal to 0. In other words, all the forces are balanced. Okay. So L is the resting length with the weight. Okay, now that we have determined what the kind of resting state or equilibrium solution of the mass spring system is, we can start thinking about oscillations. So now we're going to let u of t be the displacement from the rest length. So essentially, u of t is going to be some function which describes the equation of motion of the mass on the spring given some initial data. Okay, so again by Newton's law, which says that force is equal to ma, so F is equal to ma. Well, the acceleration associated with u is just u double prime. So m times u double prime of t is equal to all of the forces that are going to be acting on m. Okay? We all right with this so far?
Yeah.
Okay. So now the physicists just pile on a huge number of possible forces that they want to consider that might be acting on this system. So let's write them all out. M times u double prime of t. Well, first of all, there's the force of gravity acting down on the mass. No matter what, I'm always going to have the force of gravity pulling the mass down. So I'm going to have mg. That's pulling it down. The next thing is I'm going to have some force from the spring that's pulling back. So I'm going to subtract. So mg is pointing down. Now I'm adding some spring force. We know it's proportional to k. And it's also proportional to the length of the spring at any given point in time, which I'm going to write as L plus u of t. So in other words, if u of t is 1 inch, that means that currently, let me draw up here. If this is L, which is the resting length of the mass spring system, then here what I'm considering is L plus u of t, where u of t is how far away is the mass from its equilibrium rest position. Right? Does this make sense? Now why I write L plus u of t for the length of the spring at a given point in time?
Yeah, that makes sense.
It's okay. Okay. And then they add on 2 other forces. One is the force of damping. There are a lot of ways to think about this. First of all physical springs are damped in some sense, in the sense that they lose energy somehow, or that the system is being slowed down in some way. That can either be a property of the spring, or you could imagine that we're doing this experiment in water. And then all of this stuff is going to be damped because there's resistance. I mean, in air, there's also air resistance, but in water, it's kind of more clear what's going on. If you put this whole system underwater and you pull the mass down and you let it go, there should be a force associated to water pushing back against the mass as it tries to travel in any direction. So here we could think about force of damping. And then they also like to add a external force, so external acting force. So this is the damping force, and here is some acting force. So here, what I would think of the acting force is maybe someone kind of, every time that the mass gets to a certain point, you pull the mass a little bit further. Probably the best way to think about an external acting force is in a different oscillating system when you're on a swing, right? If you're on a swing and you're swinging back and forth and you're totally still, then you kind of understand what the behavior of the oscillation will be. But if you start stretching out your legs when you're going up and kicking back your legs when you're going back, then that is an external acting force that you're using to change the motion of the system. So probably the one good way to think about the external acting force is in a different equation of motion, but you still want to think about it here. Sometimes physicists want to add all these terms.
So if somebody just pulled down the weight and let it go and it was bouncing but didn't touch it again, there would be no external acting force? Or does that include the initial?
So yeah, I would say that unless you're explicitly writing how some acting force is going to come up, or there's like some important point in your model that you're trying to describe where force is being put into your system, then you want to ignore this term and set it to 0. That makes sense?
Okay, thank you.
And also, oftentimes, we would set this term as well equal to 0, the damping force. So every time that we ignore one of these forces, we make our system more idealized and less physical. Like adding in more of these forces are how we add in factors that tell us how the real world actually works. For instance, this equation, mg is a constant, L is a constant, K is some determined constant. If I move all this stuff over to one side, what I've really got here is m times u double prime of t. Here I get minus mg plus k times L plus u of t being equal to f of d plus f of a. This is a second order linear differential equation. If I set these two things to 0, then it'll be a homogeneous second order linear differential equation. And we know how to solve these. And in particular, if you set all of these equal to 0, or if you set these terms equal to 0 and it's homogeneous, then this model will say that things might oscillate forever. That's not a physical model because we know that all of the oscillations of springs or strings that we deal with eventually go to 0. And so adding in these non-homogeneous terms are ways of kind of adding more reality to the solution to the differential equation. This okay? Kinda? So this is the most general thing that we would consider. And immediately as I say that, I'll say the first thing that we should think about is the associated homogeneous differential equation, namely where we forget about these two terms or set them equal to 0. So first, consider an ideal mass spring system, which is going to be equal to m times u double prime of t is going to be equal to mg minus kl minus k mu of t, or u, not mu, u of t, plus 0 plus 0. So I'm setting the two other forces to 0. What's mg plus kl?
That was 0.
This is 0. This we know to be 0 by our calculations of the equilibrium solution, where there's no oscillation whatsoever. So I'm left with the differential equation m u double prime of t plus k u of t is equal to 0, where m is the mass and k is some constant that tells you how strong the spring is, basically. So if k is very large, I think that should correspond to a very strong spring that is very hard to compress or pull out. And if k is very small, that should compare to a very weak spring, which will extend greatly. I believe that's the case. Maybe it's the opposite. We'll find out. Okay, but in any case, m and k are constants. We know what the general solutions to this differential equation are. What are the solutions here?
It'll be the roots of the characteristic polynomial.
Exactly. The characteristic polynomial. Wow. The characteristic polynomial. Oh gosh. Is m x squared plus k, just like this. So the roots are -0. There's no x term. -0 plus or minus the square root of 0 squared minus 4mk all over 2m. And I can simplify this. What happens if I pull the -4 out of the square root?
You get 2i.
Yep. 2i root mk over 2m. The 2's will cancel, and square root of m over n is going to be the same thing as I root k over m.
Do you still have the plus or minus, or is it because we're only picking one of these anyway?
We only need to pick one of these. So you're right. I do have plus or minus here, but then I'm just going to immediately say a solution is e to the I root k over m, and then I'm going to get two real solutions out of this. Right? So this implies that a fundamental system of this equation, or of this is given by a cosine of root k over m times t plus b sine of root k over m times t. At this point, you're bored with this calculation, but are we all okay?
Yeah.
So let's, how much time do I have left? Oh, 4 minutes. First of all, what is the period of this function? Remember that both cosine and sine have periods, namely the functions just look like translates of themselves, and the periods of cosine and sine are both 2 pi. Well, if the cosine, or if the period of cosine is 2 pi, what is the period of cosine root k over m times t? Well, the period of cosine is 2 pi. So I should think about what time do I need to plug in such that I get cosine of 0, and what time should I plug in such that I get 2 pi? Or in other words, when is root k over m equal to 2 pi? Root k mt equal to 2 pi. And this is easy. Happens when t is equal to 2 pi times root m over k. Right? I just multiply by the reciprocal. So t is equal to 0 makes cosine of 0. T equals 2 pi root m over k gives me cosine of 2 pi. So the period of this oscillation is 2 pi root m over k. So first of all, this tells us something very interesting. The period is telling us, like, let me draw some graphs here. Here are some possible different pictures that we could get. We could get something like this. This is one example of a long period, or we could have very short periods that look like this, more or less. The point is, the speed of the oscillation of the mass spring system is totally determined by the mass and by the spring constant. Someone's joining. Okay. I think this is about all that I have time for today, but we're going to continue examining some special features of this mass spring system tomorrow. If anyone, so a lot of people have sent me emails, and I've got a lot of meetings these days. So if I made a plan to meet with you today, could you just write to me privately in the group chat? That would be great. I honestly forget if I planned to meet someone today. So with that being said, stay safe, have a good afternoon, and I'll see you tomorrow.
Thank you.
You
Thank you.
Thank you.
Thanks.